Hi, everyone. Let's get started. This is the final day of the course, and it is very good to see that you very dedicated students are here. I would like to thank you for coming. I would lecture even if there were 2 people or 1 person. So it makes it nice because it shows that you care enough and that you're interested enough in this material to attend. So yes, so this is the final day, and I just sent an email with sort of the end of course information. So this will sort of guide the. There isn't anything really that you have to do at this point, unless you have a homework grade that you're not happy with. And based on the list of people here, I don't think anyone is in that boat. So you all are in good shape, and I will be getting the grades for the course back to you in early August. So sometime next week or maybe the week after. So does anyone have any questions before we begin about sort of the course, about math in general? This is sort of your last chance, I realize, to ask me a question. So if you have a very general question, and we should have time sort of towards the end of the lecture. So if you have a question about math or something that you are always curious about, sorry, I'm getting an update from my computer. Yeah, now is the time. Or if you have a question from yesterday. No questions. Okay, well, if you do have a question, even like when school starts for you, you can always just email me because my email is always, it's going to be there. So you can, yeah, email me anytime, email any of the tutors anytime. I'm sure they would be happy to answer any of your questions going into the future. So let's jump into it. What were we talking about yesterday? Well, we defined the derivative, and we had several ways of thinking about it. And the first way I introduced it was the derivative as the instantaneous slope. So the instantaneous slope is sort of the slope at every point in the graph. That's what instantaneous means. The word instantaneous kind of refers to time more than space. But for our sakes, for what we're concerned with, instantaneous can refer to either one. So for any point in space or time, and it's the slope at that point. So the derivative is the collection of the slopes at each point. That's the thing called the derivative. And you can take, we talked about, I didn't write this in this list, but you can take the derivative so everything that is differentiable has to be continuous, right? If a function is differentiable, then you know it's continuous, but not all continuous functions are differentiable. And the classic example is the function that looks like this. It looks like a bird, seagull or something. And this is the function this. And there are many functions like this, but generally when you have a sharp point, your function is not differentiable. You have a jump in the derivative here. So because you can see that the slope of the tangent lines changes immediately at this point. So we talked about differentiability versus continuity. And then we also defined the derivative using the limit. And I'm about to ask you to recall that definition. And we also discussed different notations of the derivative. Y prime, f prime of x. This is the function notation. This is sort of the more casual notation. And this is the best notation objectively. This is called the Leibniz notation. And on a historical note, Isaac Newton invented everything we're talking about. He invented calculus, but simultaneously there was a co-inventor called Liebenius, and I'm not sure. Okay, this is a bad spell. That's probably not how you spell his name. Well, anyway, I'm getting close. Leibniz co-invented calculus independently from Newton, and I think maybe even a year before. It's pretty amazing how in the course of human history, like people simultaneously come up with these big new ideas. It's really incredible that calculus was calculus is a huge field. Anyway, so this is Leibniz's notation. And the reason it's so good is because unlike these notations, in this notation, you can see what you're differentiating with respect to. You know, you have this dx here. I don't know what I'm differentiating with respect to. And this really isn't a problem until you have functions of multiple variables. So say f, the function f, is a function of x, y, and z. Then I could take many derivatives. I could take, you know, the derivative with respect to x. I could take the derivative with respect to y. I could take the derivative with respect to z. And so in this case, you know, you can't use, this notation is ambiguous. So this is, you know, this notation is not useful. And that's why in multivariable calculus, you would always use this notation. And generally, well, we don't have to get into this, but maybe in your first year of college, you'll learn that if you pursue a STEM degree, like physics or math or engineering, you'll learn that the derivatives of variables, of multivariable functions, when you're specifying one of those variables, instead of using d's, you use deltas again, but not this delta, because that refers to slope. That's a finite difference. But you use this delta. It looks like a curly d. And the way you would write the derivative would be like this. So this would, and it's called a partial derivative. Anyway, we don't need to get into this at all. But this is all subtleties of the Leibniz notation, which is not present in Newton's notation. Newton sort of had his own way of doing things. So I also just want to, this is not related to calculus, but yesterday, or 2 days ago, I think on the quiz, we talked about, does nature have its coordinates? There was a true-false question. Does nature have coordinates? And can someone tell me the answer? Can someone tell me? True, false. Does nature have its own coordinates? Who got it right? Okay, Ria, tell me why. And it would be easier if you spoke rather than typed, even though I appreciate the participation either way.
We make the coordinates.
Say that again, I couldn't really hear it.
We make the coordinates.
Yeah, we make the coordinates. Yeah, so this is a philosophical point, but it's really actually important. And I have tried to highlight it throughout the course. So nature does not have an up and down. Nature doesn't have right and left. We are the people who are at liberty to impose coordinates, to hold coordinate systems up to nature. And there is no perfect coordinate system. This is a philosophical point, but it's really deep and profound. There, you know, we talked about all these different coordinate systems: Cartesian, polar, spherical, cylindrical, right? We talked about even parametric, which is sort of a mix of coordinate systems. It's not its own coordinate system. But anyway, we talked about all these different ways, and there is no perfect coordinate system, just as I think there is no perfect philosophy. You know, a coordinate system is like a philosophy of life. I don't think there's a perfect philosophy of life. A philosophy is just a thing that you use to interpret the world. It's like a map. There's no perfect map. You know, every philosophy, just as every coordinate system, will have some things lacking in it, right? It won't reveal things as well as maybe another philosophy. And a true mathematician, a great mathematician, will carry his or her coordinate systems with him or her. And this is something that one of my friend's professors said. I have a friend who goes to Loyola, and this friend told me that the professor said, you know, abandon the idea of a fixed coordinate system, carry your coordinate system with you. And I think similarly, philosophically, some of the best people, successful human beings, are able to, you know, go between philosophies and understand other people's philosophies. So this is a philosophical point that has deep meaning to me. So the answer was false. Anyway, that doesn't have to do with calculus as much, at least the calculus we're talking about. Okay, so we talked about the derivative. And can someone tell me? I'll mute everyone, which is sad because I'm about to ask you to. Okay, it sounds like the sound is gone. Okay, can someone tell me the formal definition of the derivative using the limit from yesterday? So I'm asking you, what is the formal definition of this? Someone tell me. This was the big conclusion from yesterday. Can you look back in your notes?
Is it f prime of x equals the limit as h approaches 0?
Yes.
Of f of x plus h minus f of x all over h?
Yes, very good. Thanks. And who was that speaking? I want to make sure I'm
I'm Soliana.
Okay, great. Thanks, Liana. Yeah, great. Thanks for participating. I'm taking note of who's participating because that makes a difference. The prizes, even though you should participate. Anyway, okay, great. So this is the formal definition, and we did a bunch of examples. We took y to be x, we took y to be x squared, we took y to be x cubed, and in those examples we found this general pattern that the derivative of x to some power n is n times x to the minus 1. And I even made you do some ridiculous examples. One second, people. The yard people have come to my apartment complex, and it's probably making a lot of noise on your end. So I'm going to attach some.
We don't really hear anything.
You don't hear any? Okay, well, I'm going to put headphones on because it's bothering me. It's really loud. Okay, can anyone hear me?
Yeah.
Okay, great. And I can hear you. And this is much quieter for me too. Yeah, it's annoying how they start doing the yard work here at like 7 in the morning and everyone's still asleep. It's kind of annoying, but oh well. That's a first world problem, right? Okay, so can someone tell me what the derivative of this here is using this rule?
45x to the 4th.
Good, and this is what we call, this is one example of the power rule. So this thing is called the power rule, and it's the easiest. It's very, if whenever you get this derivative, it's like thank God, it's because it's so easy. If you ever got this on a calculus test, it's really always fun and nice because it's so straightforward. It takes seconds to do, unlike other derivatives. So I didn't mention this yesterday, but I'd like to tell you today that the derivative is also a linear operator, what is called a linear operator. And this means, this is sort of, again, the definition of linearity. And we could talk, I think I defined linearity when we were talking about linear functions. And I'm just going to do that one more time so people are not confused about this meaning of linearity. If P is a linear function and you give it to other functions like f and g, say, so P is a linear function and I'm giving it by the definition of linearity, then this, the P of the sum is equal to P of f plus P of g. This is the meaning of linearity. Okay, and I'm telling you linearity. I'm telling you one sec, Adi. I'm telling you that the derivative is linear. So the derivative. So if I take so now imagine I had, instead of P, this is the same statement except D. Instead of P, I have the derivative, which is an operator. So not exactly a function, but you can think of it like a function. This means that the derivative of a sum is equal to the sum of the derivatives, right? So d dx of f plus g is d dx of f plus dx of g. And this makes it really great. But first, okay, Adi had a question that wasn't related as much, but I wanted. So English homework does count. Okay, what really I don't know. Pratik is giving me the grades for the English class. I have no idea how he's computing them. But whoever gets a B- or above in the English class is eligible. And then we're just putting our grades together. So I'm putting together a list of everyone who made a B- and above, and he's putting together a list, and we're going to see which names are in common. And those are the people who, I'd imagine most people, who are coming and participating would be making above a B-. So, and then that's totally different from the other scholarship, which is not the awards that I'm giving. That is not related at all to the IntelliChoice scholarship. That is like just for fun, for people who have done exceedingly well in the course. Okay, I hope that answers your question. Okay, so what does the linearity of the derivative allow us to do? Well, it allows us to compute the derivatives of sums of functions. For example, this function, okay, I'm going to go to Desmos and I'm going to plot this so you can, for example, There's no like good place to put that bar. It's the last day of the course. I'm still struggling here. Okay, so you see 3x cubed plus 5x. If I were to graph this, y is 3x cubed. Here, so here's 3x cubed, and I can even add. So what I'm doing is I'm adding. So I have an entirely new function. That's the sum of 3x cubed and 5x, each of which is a function, like f and g. So if I wanted to differentiate this new function, can someone tell me what it would be? By linearity, it's this, right? And now can someone tell me what it is?
9x squared plus 0.
It's not 0.
No. Or 1.
1?
Plus 5.
5.
Plus
5.
5.
Yeah, 5
Yeah.
because you have multiplied.
Yeah, it's 5, and so this is just a matter of getting comfortable with this power rule, which is really mechanical. There is no math in knowing the power rule. In fact, Anya was telling me that when her sister is 2 years older than her, when her sister was in high school, she taught her. So Anya's sister, this is not really relevant, but anyway, Anya's sister was a senior and Anya was a 10th grader, and Anya's sister showed Anya the power rule, and she like showed it off to everyone, but she didn't really know what it was. Anyway, that's what I'm saying. The power rule is a mechanical thing, and you just have to get used to it. Yeah, so the power here is 1, and that gets lowered to x is 0, to x to the 0, which is just 1, and you keep the coefficient. Okay, good. So that's an example of the linearity of derivatives, and it's very powerful because you can have all sorts of sums, crazy sums, sine of x plus x cubed, just crazy functions, right? And you can take their derivatives. It's a very powerful thing that the derivative is a linear operator. So let's calculate a few more important derivatives. We found the derivatives of all the power functions, which is it's an infinite set, actually. You should appreciate that you already know an infinite number of derivatives, right? I could ask you any power function, they're an infinite number, and you could tell me the derivative. So appreciate that much already. But let's find a few more of the important functions we've studied in this course. Wouldn't you say that e to the x is an important function of this course? I would say so. We talked a lot about it. And can someone apply the definition of the derivative to this function? So in other words, what goes here? Someone tell me?
The same thing they said before, right? F of
so you're telling me
x to the x plus.
Yeah, so you're telling me the definition of the limit. Sorry, you're telling me the definition of the derivative, but I'm asking for you to apply that definition. So I'll write the definition again here, but I'm asking you to apply that definition to this e to the x. So here my function f of x is e to the x. So can someone tell me what happens? What goes here? So this is the definition of the derivative. Can someone tell me?
E to the x plus h.
Good.
Minus e to the x.
Good. And what's in the denominator? This is the easy part. What's in the denominator?
Oh.
People, what's in the denominator?
H.
H. Thanks. Okay, so good. Okay, sorry, that was very painful. Like waiting on people to respond is tough. Okay, so but thanks. So this I can simplify a little bit, and I'll do that. So remember from our exponent rules that e to the x plus h. Well, that's just e to the x times e to the h, right? Does everyone agree? So limit as h goes to 0 of e to the x, right? And this comes from the exponent rule that if your bases are the same, you can add the exponents. So everything else stays the same here. Okay, and now this, h goes to 0. I'm going to factor out e to the x, okay? So e to the x, and what's remaining is e to the h minus 1 over h, okay? And now I can take this entire thing out of the limit, this e to the x. I can take it out of the limit because the limit does not depend, or it doesn't make a statement on x, right? It only makes a statement on h, and here are all the h's. So I'm going to take the e to the x out, and so now I'm going to say limit e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And this thing, now we have to compute what this is, And I'm going to appeal to graphing to do this. You can do this algebraically. You can manipulate this and show what this is. It actually ends up being 1. But I'm going to use a grapher again. Okay, I'm going to go to Desmos thing. Okay, so I should close the grade book. Okay, so here is that expression. Do you see it? Okay, I wrote it backwards. If people don't like that, I'll write it the way I've written it. So here I've used x instead of h, but same idea, right? Don't confuse this x and this h. Here I'm trying to plot this behavior, e to the h minus 1 over h. And I'm interested in what happens as h goes to 0. So the only difference here is that I'm using the variable x, but that's just notational. That's just what this grapher can take as an input. So imagine this at h, right? And so this is my h axis. And as h goes to 0, what does my function equal? As h goes to 0?
1.
1. And so this entire limit is just 1. And so what is my derivative? Apparently the derivative of e to the x is e to the x. And that should be kind of surprising. The derivative of the exponential is itself. And this is a profound result. I hope you realize that it's kind of surprising that the derivative of something is equal to itself, because we had a bunch of we had like power functions, and in power functions, you take enough derivatives and they, in a sense, they die off, they go to 0. But here they never. You can take an infinite number of derivatives of e to the x, and you still get e to the x. So the slope of this is e to the x, right? The slope of e to the x is itself. And the slope of the slope is itself, and the slope of the slope of the slope is itself, and on and on. So you can go on, and you'll always get e to the x no matter how many times you derive it. And generally, people write this relationship as d, and then to write the higher order derivative, you put that order here. So that the nth derivative, that's what this means. The nth derivative of e to the x is e to the x. That's this, again, using the Liebenius notation. So formally, that's the statement. And yes, as I mentioned, this is in contrast to the power law, x to the n, where the derivatives die off, eventually equaling 0. Like for x to the 4th, you take 5 derivatives, and you're at 0. For x squared, you take 3 derivatives, and you're at 0. Here, you can take an infinite. You can wait till the end of the universe, and you'll never get 0. You'll keep getting e to the x. Okay, does anyone have any questions about this result? Like the derivative of e to the x is itself. No one's unclear. Okay, good. So let's do another important function, sine of x. That's pretty important, right? We talked a lot about trigonometry, and using your intuition, you know that sine of x looks like this, right? It looks like a wave. And so you could sort of make a plot of what you would think its derivative is. Here the derivative is 1. Here the derivative is 0, right? Here the derivative is -1. Here the derivative is 0. Why am I saying the derivative is 0 here? Because I'm looking at the slope. I'm looking at the tangent line, slope of the tangent line, right? Here the derivative is -1. Here it's 0. Here it's 1. And what, if I connected these lines, what does this graph look like? Intuitively.
Cosine.
Cosine. Good, Soliana. Yeah, great. So we expect that the derivative of sine of x is cosine of x. And that would be really cool, because we would have a derivative of one trigonometric function equaling another trigonometric function. That's really neat. And so that's what we want to show here. And can someone tell me how I would, again, apply the definition of the derivative? Going from here to here, what goes here? Someone tell me.
Sine of x plus h
Good.
minus sine of x
Good. And what's in the denominator?
over h.
Good. Thanks. Great. And remember, in the last week of trigonometry, and I think everyone here, because you all are juniors and seniors, you all know the double angle property. Can anyone remind me what sine of x plus h is? We derived this, even if you haven't seen this before, but I expect everyone to know this. What is sine of x plus h? Do people know this? We did spend some time on it. I derived this for you. And should I just tell you? Okay, it's sine of x times cosine of h plus sine of, plus cosine of x times sine of h. So if you don't remember where this comes from, just Google the double angle property. Okay, and there's one for cosine of x plus h, which we're going to use in just a bit. Okay, so I've applied this property, which I derived for you, and I'm not going to derive it again because that takes a lot of time, but I expect people to know this. And now I'm gonna write that here. So sine of x cosine h plus cosine x sine of h, watch out there, minus the sine of x all over h. And now I'm going to factor out the things that are in common. So sine of x is common here, right? So this is sine of x. So I'm taking out sine of x from the first term and the last term, right? So I have remaining cosine h minus 1 plus cosine x sine of h over h. And remember, people, I'm being sloppy. I'm not writing the limit as h goes to 0. I always forget to do that. Limit as h goes to 0. Okay, and now just as the derivative is a linear operator, the limit too is a linear operator. So I can break this limit into its corresponding, into the sum, right? So this is equal to the limit as h goes to 0. And again, sine of x I can take out of the limit because sine of x doesn't have an h in it, and the limit is a statement that includes h, not x. So this is equal to sine of x times the limit of this thing, cosine h minus 1 over h. And then here's the second part, plus, again, cosine x comes out of the limit because the limit doesn't make a statement on x, and times limit of sine of h over h. And again, people, I'm going to appeal to graphing. I'm going to appeal to a graph to find what these limits in the brackets are. And so these are all pretty intuitive things, actually. Once you study, can you take out sine of x? I did. I took out sine of x here. Look, this was the first term.
But sine of x is not a factor of cosine x sine,
Well,
which
that's
is
why
a term.
sine of x is not a factor. Look. Okay, did you follow
Second term.
the second term? No, this was cosine x plus sine of h. This was, sorry, if my handwriting is bad. This is an h. I had written x there and then I scribbled.
Yeah, so can you factor out a sine of x then?
Yeah, I can. Well, so look, all I did was I wrote these two terms together. So this is term 1 and term 2, and I wrote these two. So I factored out sine of x from these two terms, and I factored out, so to speak, or I just rewrote term 3 here. And then you could obviously, because you can break up a fraction like this, right?
Yeah, okay.
So that's what I did. Is that clear? Yes?
Yeah.
Okay, great. Good question. Good question. Okay, so what are these limits? Again, I'm going to appeal to graphing. And so I have a graph. And again, this grapher only accepts x as an argument. So imagine that these things were h. Don't confuse this x with the x, with this x. Imagine that the x's in the grapher are h. So cosine of h minus 1 over h. Let's see what that is. And we're interested in what happens as h goes to 0. Look, as h goes to 0, so here's my h-axis. What does the function equal? What does this thing approach?
0.
0, good. And so this thing is 0, which kills off this sine of x, anything times 0 is 0. So this entire thing is 0. And limit as sine of h over h. This is actually a very famous limit as h goes to 0 that you'll study a lot. And here's a graph of sine of, imagine again that this x's are h's. What does this thing approach?
1.
1, good. And so this thing is 1. This entire limit is 1, and anything times 1 is 1. So therefore, my derivative is cosine of x. And that's exactly what we wanted. We wanted to say that the derivative of sine of x is cosine of x. So we use the limit, the definition of the limit, and we use some considerations from graphing as an aid. Technically, you don't even have to do that. There are formal ways of doing this. We just don't have time to do that. So graphing is a great aid. So indeed, the derivative of sine of x is cosine of x. That's exactly what we anticipated from our naive little graph here, our simple graph, just plotting out the slopes of the tangent lines at important points. So I hope you can now see the appeal of one of the many appeals of graphing. So this is our conclusion. And I'd also like to do this very quickly for cosine of x, and I'll do this faster because it's a very similar process. Okay, so I'm not going to wait for people, but cosine of x is the limit. The derivative of cosine of x is the limit as h approaches 0, cosine x plus h minus cosine x over h. And now we're going to use the double angle property for cosine, which is this, cosine h. So again, if you don't remember where this is coming from, review the double angle property. You should have learned that in pre-calculus or some trigonometry class. And now here's the part that someone was confused about earlier, the analogous part for this proof or derivation, where I'm going to factor out the cosine of x from these two terms, and I'm going to leave this term alone. So factoring out cosine x from the first and last term, I have cosine h minus 1 minus sine of x sine h all over h. And now, see people, look, no one caught me. I keep forgetting to write the limit. Limit. There we go. Not minus, okay, Soliana said minus sine of x. Where? Can you help me? What, did I mess up? Soliana. Oh, you're saying the answer. You're saying the answer. Okay, Soliana, have you taken calculus before? Yes. Oh. Okay. Well, that's good. That's good. I'm very impressed that you know this. That's awesome. Okay. Although, like, yeah, I don't want to. Yeah, it's special for the people who are seeing this for the first time. Okay. So again, using the linearity of the limit, I can take out the cosine x. Sorry, this is a bit sloppy, and I'll write what's remaining, right? Minus sine of x limit sine of h over h, and we just found that limit of sine of h as h goes to 0, sine of h over h. This is just 1, so this entire thing is 1. So I'm left with so the sine. So yeah, so this is 1, and similar, and just as we had found that sine of h minus 1 over h is 0, I can also. Actually, no, sorry, we did not say that. This is the same. This limit is the same as this one, right? The same thing appeared, and so this limit is 0. So the cosine term dies because cosine times 0 is 0, and I'm left with minus sine of x times 1, which is minus sine of x. So as Soliana said in advance, the derivative of cosine is minus sine. So these are the very important derivatives of calculus, and this is really cool because we've shown that the derivative of cosine is minus sine and the derivative of sine is cosine. Note that, don't forget this minus sign. Okay, this is important. And in a sense, it's a two-way street between sine and cosine. Well, one derivative gives you the other, and the derivative of the other gives you one. Okay? So I urge you, as you go through your calculus class, and I'm sure Soliana can attest to this, that you should make a table of all the derivatives you know, and these are all the derivatives we know. Okay? We found the derivative of the power, we found the derivative of the exponent, and we found the derivative of sine and cosine. So I'll give you just 10 seconds to copy this down if you want, and to ask any questions if you want. Okay, that was about 10 seconds. Now, let's sort of move on to the next juncture. This would be the second semester. So we just covered in very crude detail what maybe you would cover in one semester, or maybe 5 or 6 months of a calculus class, of an introductory calculus class, like AB or BC calculus. And now we're going to talk about the second part of what you'll cover, which is this idea of the inverse. Well, okay, so it's not the idea, that's not all you covered. What you actually, the field of what, everything we've covered so far is in this field of what's called differential calculus. And there is another field that is like the inverse of differentiation. And this is really cute, actually, because you might remember it's your preschool or kindergarten or first grade days when you spent maybe 6 months learning addition. And then you might remember how you spent the next 6 months learning subtraction, or like half the school year is spent on addition, half the school year is spent on subtraction. Yes, yes, the inverse of differentiation is integration, and that's what I'm building up to. And then in third, maybe, I don't know, for me it was like second, third grade, when I learned how to multiply things, we spent 3 or 4 months on that, and then we spent 3 or 4 months on division. So, you know, then in, I don't know, algebra 2, you probably spent a few weeks on exponentiation, and then you also learned about logarithms. So all these things are inverses of each other. And again, in your life, you're about to receive, you know, this sort of inverse, this notion of inverse. It's you just haven't realized. I mean, it's really been going on all your life. You just haven't realized it, and here it's about to happen again. So the inverse of differentiation is what we're about to call, and it's called integration. So right now, integration is just a word, but it will become integration. It will become an entire field of calculus called integral calculus too. And I'd like to introduce this idea of integration by asking you, what is the opposite of taking the slope? So if I had the slope, you know, so say I have this general curve, f of x, again, and I wanted to find the slope. So I wanted to find f prime of x. What I'm doing is I'm approaching this tangent line. You know, I'm bringing these 2 points closer and closer together. Now this is a hard question to answer because it's sort of abstract, but what is the opposite of finding the slope, of bringing points very close and close together and finding sort of the edge of a graph? Yes, integrals, finding the area. Good, thanks. Finding the area under the curve is in a sense the opposite of taking the slope of the curve, or how steep the curve is. So finding the area under the curve, that is this area, right? This area, finding this area is in a sense the opposite of finding the slope, or you know, essentially taking the derivative of this curve. And so okay, so I don't want to jump too far ahead as I introduce these things. So yes, you're right, taking the area under the curve. And maybe I will introduce this. So this black line is f of x, right? And this blue, okay, well I'm gonna erase my curve here, my area. So f prime is this line. And if I graphed f prime, I'll do it in blue. If I graphed f prime, it would look something like, in this region, it would look something like this, right? Because this is kind of, in a sense, you know, constant acceleration. So taking its first derivative, you know, it's roughly parabolic here. Taking its first derivative would give me a line. Going from here to here, right? So going from here to here, I've taken a derivative. Going back, I'm taking an integral, right? So going from f to f of f prime, you're differentiating. Going from f prime to f, you're integrating. So if I integrated this line, I would get this curve. So this is the notion of the inverse. Sorry, I can't write here properly. Okay, I hope this makes sense. I wanted to introduce integration as the inverse of differentiation. And in your calculus course, you might hear this word antiderivative. They're going to introduce this word antiderivative. And this is really the integral. But the reason they use this word is to highlight the fact that it's the inverse of differentiation. So just as, now formally, so we have this rough intuitive sense of what the integral is. It's the inverse of differentiation. And now formally, remember that the derivative is defined as the limiting case of the slope, right? It's the instantaneous slope, and that's precisely what this statement is. You know, the limit as the change in x minus x1, or h, you know what I was calling h, as, look at this, people, I made an error. As x goes to 0 of the slope, which is our high school understanding of slope, middle school understanding of slope, right? Just as the derivative is defined this way, the integral is also defined as, so this is the symbol for the integral. It's a big S, right? This is an S, Newton's notation. And it's, so ignore this. I'll tell you what this means in a sec. But the integral is defined as the limiting case similarly. Now, I want you to look at the similarities here. As this finite difference, x, delta x goes to 0, of this sum. Look, this is a sigma. My sigmas aren't too good. It looks like a backwards 3 or an E or something. It's supposed to be an S, capital S. Okay, don't worry about that. Sigma, it's capital sigma, okay, in Greek. It should be written like that, but I don't have the patience for that. Okay, so it's the limiting case of this area, y times delta x. Okay, so this thing is called the Riemann sum, and we're not going to talk a lot about what the Riemann sum is really in calculating Riemann sums, but this is the Riemann sum, and when you take the limit of the Riemann sum, you get the derivative. Just as when you take the limit of the slope, you get the derivative. So I want to make this parallel very clear, because this was not made clear to me. No one ever wrote this out for me. I wish someone had written the derivative as the limit and the integral as the limit when I was in high school, when I was in 12th grade, but no one did that for me. So I hope this is useful. So here's the things that you're taking the limit of. These are things that you learned in middle school. Literally, the Riemann sum is just base times height. That's literally what this is. Y is your height of your function, and the base, b, is your change in x. That's how far you are this way. So here's y, here's x, right? So base times height, literally, or length times width, however you want to think about it. And when you sum up all of these little rectangles, and you take the limit as this finite difference goes to, you let this difference go to 0, then you get the integral. And just as we denoted, just as the deltas here became d's when you take the limit, you can see that this delta x became dx, right? And instead of using the sum sign, we use the integral sign, right? That's what this integral, that's what the sign means. It's really a sum of infinitesimal rectangles. So, okay, I'm throwing a lot of big words at you. Let's draw a picture and sort of understand what's going on. So the Riemann sum is the sum of a bunch of rectangles under this curve. So I could draw, maybe 4 or 5 rectangles that approximate this curve. Okay, and I'll try to draw them of equal width, so you can see here. Look. So I'm taking a point on the graph and I'm drawing rectangles. And if you computed this, a middle schooler can do. If I told you the right dimensions, right? If I told a middle schooler the correct dimensions of each of these rectangles, a middle schooler could sum up. So say each of these bases is 1. So here, delta x is 1. That's this delta x here. Delta x is 1, and my height is y. So that generally is y. That's exactly what the function is. But say I gave you the height of each of these rectangles. So say this is 5, 6, 5, 4, 4, 5, and 6. Well, literally the area of all of these rectangles, which is not exactly the area under this curve, right? Because you have all this little error here. You have this error, this error, this error, right? You have this error, but roughly the area under the curve would be 5 times 1 plus just the sum of the areas of these rectangles. 5 times 1 plus 6 times 1, on. And because your base is 1, you don't even need to factor that in. It's just literally the sum of the widths. That's what your area would be. 5 plus 6 plus 5 plus 4 plus 4 plus 5 plus 6. That would be the area under this curve, and it's in units squared. And if you could sum this up. This is 15 plus plus 10, so 25, so like 35, I think. Okay, I could have done it wrong. Anyway, a middle schooler could do this. That's what the Riemann sum is. It's very simple. And now, as I follow the definition of the limit, the definition of the integral, if I let these rectangles, if I let the width of these rectangles go to 0, right? So literally, I'm going to erase this stuff. Thanks for your patience as I do this. So literally, I'm going to make smaller rectangles now. So if I have tiny rectangles, and you can imagine, I'm not going to do this for the entire graph, but you can see that my error has gone down, right? Because remember how when I had big rectangles, I had big errors. This was my error. Now you can see my error is a lot smaller because I'm taking smaller rectangles. And the idea of the integral is if you take an infinitely thin, if you essentially let this go to 0, if the width of these rectangles goes to 0, then your error also goes to 0. Sometimes the error is denoted by epsilon. Okay, So the statement is that when the thickness of the rectangles goes to 0, your arrow also goes to your error. Sorry, I'm drawing arrows and saying error also goes to 0. So this is the definition of the integral. Okay, does this make sense to people? This is sort of the big picture of what I really wanted to cover today. What is an integral? Because yesterday we spent on derivatives mainly. So does this formal definition of the integral make sense? The limiting case of the Riemann sum. Yes, no, maybe. I want to hear your feedback. Yes, okay, good. Good. Okay, so thankfully, once you know the derivative, you know the integral because they're opposites. In the sense that we don't have to go computing integrals theoretically, right? Like you don't remember when you had the derivative, we calculated derivatives by applying this definition. You don't have to calculate integrals by applying this definition. That would be a pain. That would be really painful. And the reason you don't have to do that is because these things are intimately related. These things are inverses. And if you notice that, if you take into account that derivatives and integrals are inverses of each other, then you already know integrals. Because if you know the derivative of f of x is g of x, by this idea of the inverse, you know that the integral of g, so integrating both sides, you know that the integral of g is f of x, right? This is the statement that the derivative is the inverse, or the integral is the inverse of the derivative. They're inverses of each other. And this statement, what I've drawn right here, I wrote this as 2 lines, but you could also write this as 1 line, and sometimes it's more clear to people if I write this as 1 line. So if I can integrate. How did I get this statement? Well, you can integrate both sides of this equation, right? Again, algebraically, you can do anything as long as you do the same thing to both sides of the equation. That's my reasoning here. And here's where I'm using this idea of inverse. Because the integral and derivative are inverses of each other, this left-hand side is just the integral of the derivative of f of x is just f of x, because integral, in a sense, they cancel out. Integral and derivative cancel out. And so f of x, which is on the left-hand side, is equal to the integral of g of x. And that is this statement here. So what I'm telling you, people, is that if you know that the derivative of f of x is g of x, then you know what the integral of g of x is. And it is, in fact, precisely f of x. And this statement, the statement that the derivative and integral are inverses, is called the fundamental theorem of calculus. So you might want to write that down for your quiz. Just that the derivative and the derivative and integral are inverses of each other. So let's put this into practice and compute our first integral. If we know that the derivative of sine of x is cosine x, then what is the integral of cosine of x? Can someone tell me?
Sine of x.
Yes, and the way I do that is I'd apply the fundamental theorem of calculus. If you're confused, I would do this. I would integrate. So look, to get the integral of cosine of x, I can integrate this entire equation. And that's what I'm doing here. I put an integral sign here, I put an integral sign here. And because this d of x is always there in the integral, because the integral and derivative are inverses, in a sense, they cancel each other out, and I'm left with sine of x. And this is not actually precise, okay? I actually should, I'm not gonna get into this, but when you integrate things, you actually get an error of some constant c. And I don't want you to worry about this yet, because this is sort of secondary to our discussion. I just want you to get the big picture of what the integral is. So for now, I'm going to essentially let those arbitrary constants equal 0 for the sake of the rest of this discussion. But for those of you who have seen some calculus, just bear in mind, no, I'm not making a mistake. I'm just not writing c. Okay, good. So the integral of cosine of x is sine of x, just as the derivative of sine of x is cosine x. Can someone tell me then? Okay, so I'll give you a derivative, and I want you to tell me the integral. That's sort of the exercise here. So you know that the derivative of, say, x squared. Can someone tell me what that is? Easy.
2x.
2x. So can someone tell me what the integral of 2x is?
X squared.
Good. And again, I'm not writing that constant. So integral of 2x is x squared. Good. Now, I want to formalize this relationship in particular with general powers. Can someone tell me what this is?
X.
Good. And so what is the integral of x? A pretty important integral if you ask me.
Half x.
Yeah, 1/2 x squared. And so good. So people are, okay, so I want you to take note of this, okay, that the integral of x is 1/2 x squared. I'm going to ask you another derivative. Let's say, can someone tell me what the derivative is?
X squared.
Good. And so what's the integral of x squared? Oops, sorry.
1/3 x.
Good. This is literally a piece of cake. Literally I'm telling you the answer. Literally the integral is what you're, because I just want people to get comfortable with this. Good. Again, I'm disregarding my arbitrary constants for those of you with more experience. Sorry, my screen keeps jumping around. Okay. Let's do one more. This is a fourth, 1/4. What is this?
X cubed.
So what's the integral of x cubed?
1/4 x to the 4th.
Good. Now, are people seeing the pattern? What happens when I integrate a power of x? Look, I integrated x, I got 1/2 x squared. I integrated x squared, I got 1/3 x cubed. How do I get from here to here? Can someone derive a pattern for me?
Like the opposite of
sorry.
the power.
Okay, okay, good. Wait, one sec. Someone caught an error. I miswrote this. Yes. Okay, so what were you saying? The opposite?
Like you do the opposite of the power rule.
It is. It's the opposite of the power rule, right? So, and that makes total sense, right? But generally, you could write that the integral of x to the n, right, is, can someone tell me this? Like, yeah, you're right. You see the pattern, but I want like a formal relationship. So go ahead.
Is it 1/n+1?
One.
X n+1?
Yes, what you said is correct. 1/n+1 times x to the n+1. Very good. So now I could ask you something ridiculous, like what is the integral? So what, at this point, you're still thinking about things in terms of derivatives because that's probably what you're comfortable with, but I want you to get equally familiar, and this will come with practice. I want you to get equally familiar with taking an integral of something like a power function. So if I asked you something ridiculous, like the integral of, okay, let's not, okay, what's the integral of x to the 1,000?
1/1001 times x to the 1,001.
Good. And you can always check your answer by differentiating this, right? If you differentiate this, you better get this. And the thing inside the integral is called the integrand, okay? So by differentiating the results, you should get the integrand. And indeed, if you differentiated this, you get 1,001 divided by 1,001. So now I'm using the power rule, our old friend, the power rule. And 1,001 minus 1, and that's indeed 1 times x to the 1,000, which is x to the 1,000. Good. So lastly, I'd like to tell you, the last thing I'll say in the entire course, is that the integral is also linear. Just as the derivative is linear, the integral is linear. And this makes sense because the derivative and integral are inverses of each other, so they better sort of have the same big mathematical properties. And so the statement of linearity of the integral would be that the integral of a sum of functions f and g is the integral of f plus the integral of g. And so just one last example would be find the integral of cosine of x plus x to the 5th. Can someone do this for me? Last example of the entire class.
Sine x plus 1/5 x to the 4th.
Plus, be careful.
Oh, 1/6 x to the 6th.
Yes, good. And again, you could add some arbitrary constant, but for this introduction, I'm letting that be 0. Good. Okay, good. So now you know what the integral. This is pretty cool. Now you can integrate really complex things. Okay, people, I'm going to send the last quiz. I don't mean to be like melodramatic. Yeah, last quiz ever. And I don't think there's any integration on this quiz. So really just formalizing your understanding of the derivative. Okay, people, it was great to work with you and teach you. And thanks, Long. Okay, people, keep in touch, and you can email me. Yeah, you're welcome, people. I wish like I had like more social media so people could keep in touch, but I don't. I have a Facebook, but don't even bother. I don't get on there. But if you want to get in touch with me, if you have any questions, or if you want a recommendation letter for college or something, let me know, or what, I'm happy to help. So, and Ascension wants the quiz from yesterday. Okay. Yeah, thanks for your thank you notes. That's very kind. The quiz from yesterday. I'm sending it. Just a sec. Love you too, Lon. Thanks. I'm glad you enjoyed the course. Okay, Ascension. I'm going to privately send this to you so people don't get confused. Okay, there it is. I just sent it to you. And yes, everyone, you're very welcome. I love you all. And all the tutors love you a lot. In fact, like, I don't know if you people knew, but many of us actually like share the same apartment area. So we all sort of, we don't, yeah. So we like have, we're socially distancing with the world, but we don't per se distance with each other. So like Anya and Patricia and John and Chris, like we all like are somewhat in touch with each other in person, which is nice. And we talk about you all. So yeah, so it's a lot of fun. And yeah, okay. Thanks, everyone. I'm going to end the meeting. So this is not like a dramatic thing. And keep in touch. All the best. Bye.